This section of videos in analog electronics is going to be on resistor circuits. In particular, we'll be revisiting several of the simple resistor circuits which we built and tested in Physics 110, the first quarter of the course sequence, and adding a little bit of a theoretical framework which will allow us to generalize to more complex circuits, and in particular the situation where we want to build a circuit that manipulates a signal coming through it. By manipulate, I might mean amplify. It's an audio signal, could make it louder or softer, or filter it, or make some other modification by inserting a plug-in or a transformation circuit. We'll talk about how those work in coming weeks. Today we concentrate on some of the basics of just resistors in circuits. So we start by reviewing the single resistor circuits and how to measure current and voltage, how that determines the power that goes through a resistor. And we'll talk about how you can deal with more complex circuits with more resistors in them, the limiting cases of resistors in series and parallel, and in the very special case of the potentiometer or voltage divider circuit. And we'll use this example to discuss not just equivalent resistors, but whole equivalent circuits where the voltage and resistance change as you hook them to subsequent components. We're going to introduce the idea of Thevenin equivalent circuits to make this conceptual jump easier, and discuss the origin of the loading problem. That is, how when you attach a new component to a circuit, it changes the properties that you have of the unloaded circuit. And then we're going to talk about the solution to that problem, which is using the operational amplifier op-amp, in particular its use as a follower or buffer. And we'll basically review the three different properties of op-amps we'll be using in this course: followers, comparators, and amplifiers. This topic will be continued in the next series of lectures. So in a single resistor circuit, we start with a power supply. To make things simple, we'll say we have a DC supply with one end held at 0 volts and the other at some potential difference above. This might be 9 volts from a battery or 5 volts from another power supply, but these are both DC voltages separated by some potential difference. And a resistor, here R1, is connected between the two terminals. And so, of course, current flows through this resistor, and that current is related to the value of the resistor in ohms and the voltage across it by Ohm's Law, which is V equals IR, or voltage equals current times resistance. The power, as we've discussed in Physics 110, is the product of the voltage and the amount of current through it. We used, to begin with, the analogy of a waterfall in Physics 110, which is that the voltage is like, say, the height of a waterfall, and the current is, of course, the current that goes through it, and the power of the waterfall is the product of those two, that is the current times the voltage, gives you the power of the circuit. So this leads us to the result that resistors with very small values can draw a lot of current and therefore have a lot of power dissipated in a circuit, with the limiting case being a resistance of 0, which we call a short circuit, in which case the reservoir might even be quickly drained, and the other limiting case of an open circuit, which of course is that resistor is equal to infinity and no current flows whatsoever. Now, to measure the voltage, this can be done by using a voltmeter. Typically, we use a digital multimeter configured in the voltage mode, and you use two probes to measure the voltage across the resistor. So voltage is measured across the circuit. Current, on the other hand, if it's to be measured directly on a multimeter, this is accomplished by switching your multimeter to current mode or amp mode, and breaking the circuit and inserting the meter into the circuit itself. In these simple circuits where there's no branches, only one source of the current and one sink, you can choose to break your circuit anywhere either, for instance, between the resistor and ground, or between the voltage and the resistor. The current will be the same everywhere in these circuits. And so that's how you would directly measure current. To measure current and voltage at the same time, you would have to have two meters. One voltmeter would measure the voltage across the resistor, and then a current meter inserted on either side of the resistor would be used to measure current. This gives you then an independent measure of voltage and current. Now, there's no reason to ever build such a circuit if you truly have a resistive element. And resistors that we grab and have color codes sorted into bins and boxes, we usually presume those are very, very good resistors. That is, they obey Ohm's Law very, very well. So that actually measuring the voltage would be sufficient, because when you place that resistor across, you can calculate the current that's running through it from Ohm's Law. However, we've seen a few examples where this isn't the case, where we have elements which don't exactly follow Ohm's laws. These would be LEDs, light bulbs, thermistors, photoresistors, other sensors of different types, and in some cases, some components which simply may not act like resistors very well at all. So now we're going to start talking about more complex circuits than just a single resistor. And with a single resistor, fully characterize it with that current or that voltage and the use of Ohm's Law. What happens when we have two resistors in series? Well, as we saw in Physics 110, you can really think of these two resistors as being sort of a substitute or equivalent to one other different resistor. So if you have a 10 ohm resistor and a 20 ohm resistor, you could say, well, this just taken together is like a 30 ohm resistor. And that's expressed mathematically by replacing those R1 and R2 resistors in series with an equivalent resistor, which I've called R sub EQ for equivalent, and it would just be equal to R1 plus R2. And so we can convert that more complicated arrangement into just a single circuit element. Now, this is a convenient thing to do if, say, you needed a 30 ohm resistor and all you had was a 10 ohm and a 20 ohm. But it's far beyond that in terms of its utility, as we'll see in a couple minutes. The current through this equivalent resistor then is very easy to calculate. It's just as if we had a single resistor where the resistance was equal to R equivalent. We would take the voltage across and divide it by this equivalent value of R1 plus R2, and that would tell us the current that ran through the circuit, and therefore the current that ran through both resistors. Now, what if we wanted to go backwards and understand what is the voltage drop on each resistor individually, R1 and R2? And we already know the current, which is the same through both of them. But what is the voltage on each one? Well, we would apply Ohm's law to each resistor individually. So I just figured out that current I, and that is voltage in over R equivalent, and R1 multiplied by that current would give us voltage 1. That is the voltage that we'd measure with a voltmeter across that first resistor. So V1 would be I, which is V in over R equivalent, times R1. Similarly, V2, the voltage across the second resistor, would be that current through this entire circuit, which is again the same all the way around, times R2. So that's V in over R equivalent, that's our current, times R2. Now just substituting in an R equivalent for being R1 plus R2, we would come up with these expressions for the voltage across the top and the voltage across the bottom resistor. Let's think for a moment about how exactly this works. Let's think about, in particular, just a couple of what I call limiting cases to see if it makes sense. By that I mean we're going to ask ourselves, what is V1 and V2 in situations where we already know the answer? Well, one of the easiest is if there's simply no voltage at all. We disconnect the battery or the power supply. In that case, V in is 0 volts, and 0 volts multiplied by this expression, whatever it is, simply gives us 0 volt output, which makes sense. If I don't connect the power supply, I read no voltage out. The same, of course, happens for the second resistor. What are some other things to notice about this equation? Well, one of them is the units. We want to make sure we have voltage coming out, and here we have a voltage in. So it's no surprise that this ratio of resistances is unitless. The units would be ohms on top for R1, and ohms plus ohms, which is still ohms as a unit, for R1 plus R2. And ohms over ohms is simply equal to 1. The units cancel. If you have a unit of volts in, you'll have a unit of volts here for V1, and the same for V2, of course. Let's think about just a couple other limiting cases. And particularly, let's think about the case where V2 is very, very small. In fact, let's say V2 is actually just replaced with a wire, so a resistor of 0 ohms, if you will, so that R2 equals 0. Well, if R2 equals 0, what's V1? Well, if we put 0 in for R2, we have R1 over R1 plus 0 times V in, or simply V in equals V1, which makes sense if we have connected ground to the bottom of V1 by making R2 equal to 0. Let's look at the other equation for a moment. Let's say again R2 equals 0. What should V2 be? Well, we know it's connected to ground, so the answer should be 0. We'll check it. It makes sense if we put a 0 here in the numerator for R2, this entire expression is 0, multiplied by V in is still 0, and V2 is 0. And I'll leave it as an exercise to the students in this class to verify in their own minds that, furthermore, if you were to take a R1 value equal to 0, that is, replace this first resistor with just a wire, that you would also end up with reasonable answers for what V1 and V2 should be. One last limiting case to talk about. It's always good to go through these sorts of situations whenever you have some new results. And that would be, what if the two resistors are the same? Well, if R1 was equal to R2, this ratio would be 1/2. This ratio also, R2 over R1, would be 1/2, and we would find that V1 would be equal to half of V in, and V2 would be equal to half of V in as well. In other words, half the voltage drop would happen halfway down the equal resistance network, and the other half of the voltage drop would happen the other half of the way. A couple other limiting cases you could think about would be the situation of an open circuit, that is making R1 equal to infinity, or R2 equal to infinity, that is having an open circuit, and what should happen in those cases. Again, that's something to think through a bit on your own. So this is the idea of equivalent resistors, that we take a initially complex problem, slightly complex in this case, just two resistors in series. We turn it into a single equivalent resistor where we can readily apply Ohm's Law, in this case to figure out the current through the circuit. And then we go backwards and apply those results to the more complex configuration, in this case, the resistors individually. Let's do another example of this idea of equivalent resistors. Here we're going to consider two resistors in parallel. So R1 and R2 both hooked up across the same power supply of voltage V in and 0 volts. Now in this case, we know the voltage is the same. Waterfall has got to get from the top to ground, but it can take one of two different paths to go there. So it's like two waterfalls in parallel. One channel might be bigger than the other channel, or in other words, the resistors might be different sizes. So maybe this one is 100 ohms R1 and this one is, say, 200 ohms R2. So what's the equivalent resistance in this case? Well, what's clear is that although the voltage is the same, the drop is the same, the currents are going to be different. There'll be one current through R1, labeled I1, and a second current through R2, labeled R2. And in the end, the current up here coming out of the power supply has to be I1 plus I2. The currents have to add because the current can't go anywhere except take one of these two different routes. And the current here returning to ground has to also be equal to I1 plus I2. So from Physics 110, we'll recall the answer to this problem. And you can go back and rederive it and try to re-understand it a little bit. We'll talk about some of the physical implications of it here in a moment. But the equivalent resistance is given by this inverse relationship here in equation 7. The reciprocal of the equivalent resistance, that is the resistor that we replace R2 by, is given by the reciprocal of the first resistance plus the reciprocal of the second resistance. And so following this formula, we end up with a situation here for resistors in parallel that actually appears to be the same as the situation for resistors in series. The only difference is that the actual value of the equivalent resistor is very different. Now, to calculate the current through the entire circuit for these resistors in parallel, we would take the voltage in, which is the total voltage drop in the circuit, divide it by this equivalent resistance. So we're neglecting the fact that, in fact, this is made of two resistors, but we know that there is a total current I that must flow through both of them. Substituting in 1 over R equivalent, we get this expression here, equation 8, for the current through the entire circuit. Well, let's go back and look at now the original more complex circuit for resistors in parallel. We can use the fact that all the voltages are the same to calculate the current through each resistor individually. So V in has to equal I1 R1 by Ohm's law applied to this one resistor element, and it also has to equal I2 R2, which is Ohm's law applied to this second resistor element. Furthermore, if we were to combine these into the equivalent resistor, Vn also has to equal, as we had on the previous page, equation 8, equal to I times that equivalent resistance. Therefore, if all of these are equal, we can set any of them equal individually. So I1 would have to be equal to I times that equivalent resistance over R1, or V1 over R1. And I2, similarly, would have to be V2 over R2, or R equivalent over R2 times the total current. This is just an algebraic consequence getting from 9 to 10. Make sure you're clear on how those algebraic steps work. After you've gone through the algebra, you'll be ready to do some practice problems. I'll post a few practice problems as well. But the concept is still the same, or should be kept at least very clear in your mind. The idea is to break down something complex to something simply recognized, and then reinvert it to understand what's going on in individual components. That's a problem-solving approach that we take to analyzing circuits, but more importantly, to designing them and understanding schematics. Let me also introduce one other equivalent resistance circuit, which is extremely important for our purposes, which is the loaded voltage divider. Now, the voltage divider consists of two resistors in series, R1 and R2. But then across the bottom resistor, R2, we're going to attach another resistor, which we'll generally call the load resistor, or R load. And the question is, what is the current and voltage through each resistor on this page, all three of them, as well as the power dissipated, the current times the voltage in each resistor, with and without that load resistor connected. So with and without this load resistor connected across this bottom resistor, what are all the parameters, voltage, current, and power dissipated in that system? To do that, we'll be breaking it down into two cases. First, of unloaded, which is basically the situation of resistors in series, and then doing the more complex problem. And the way you'd proceed to do that is do resistors in parallel to make a equivalent resistor between R2 and R load, and then resistors in series to add R1 to this new equivalent resistor to get a new equivalent resistor for the entire set of three. Having done that, then work your way backwards one at a time to figure out the current and voltage in each individual component. Now that's a lot of effort, and I'll be giving you some examples on how to do it. But the reason to go through the exercise at least once or twice is to understand the importance of this load resistor and how adding a load resistor changes the way the circuit would have behaved otherwise. And that's a really important thing when you're building modular electronics and hoping to just go and use patch cords to plug in and out loads. You want to know, are they going to change what was going on upstream or not?